All right, so we're going to talk about chemical reactions using the demonstration that hopefully you just viewed. Um, and so what we want to do is use this example to talk about the meaning of a chemical reaction, and then in a later one we'll talk about balancing them and everything like that. But this is just our introduction to chemical reactions. And so we did this explosion of, it was actually ethanol. It can be methanol or ethanol. I used ethanol, but we're going to, for this one, use methanol for the writing of the reaction just because it will work better. So that was called the methanol cannon. And that's kind of a cool reaction. I hope it was fun for you. It was fun and exciting for me. But this is the formula for methanol. And that methanol, when it's in the uh, cylinder, was actually a gas. So when we add states of matter, we'll put a little G for gas. And then with oxygen, so I'm going to write 3/2 of a molecule of oxygen. We'll talk about balancing later. Right now, I just want to kind of talk about the meaning of it. And then we would get carbon dioxide. It's a combustion reaction, so we're burning the carbon to carbon dioxide gas, plus we'll get some water that's also a gas in this case. And so that's the reaction, and it's balanced. We'll learn how to go back and forth on balancing these. But some of you who've had some chemistry before might not necessarily like that 3/2 on there, because a lot of times we're taught in intro chem to always have whole numbers, and it's fine either way. Uh, Sometimes you'll be specified, or a question will specify that we need to write it with all whole number coefficients, and that's the usual way we'll do it. There's other times when it makes sense to just have it how it works out. This makes it easier to balance actually. And then if we're only interested in one molecule of that. But we can write this reaction a different way to make that a whole number. Just multiply everything by 2. We'll have 2 of the methanols plus now 3 of the oxygens burning to give 2 carbon dioxides, plus that would make for 4 waters. And so that's a chemical reaction, and what we want to do is talk about the meaning of that reaction and the conventions we have for it. So the first thing is that, the first semester we're just talking about reactions that go from left to the right. Second semester we'll talk about reactions that are more of a balance. But regardless of what kind of reaction you have, the things on the left are called the reactants. Even if a reaction is running backwards, which we won't have any backwards reactions in first semester, but just so you get the idea, it doesn't really matter what's happening. Everything that's on the left are called the reactants, and everything that's on the right are called the products. And in fact, this one-way arrow that we're going to use indicates that we're starting with the methanol and the oxygen in the air, and we're ending up with carbon dioxide and water. And for the first, half of the semester or whatever, we're going to treat all these reactions like they are 100% go to completion. And that's called a stoichiometric reaction. And a lot of what we do are called and we'll talk about stoichiometry some more later when we do the grams to moles and all that back and forth. But this reaction then is just methanol plus oxygen, carbon dioxide, and water. It's a fun little explosion. And yeah, it's kind of cool. But the meaning of the reaction, what this reaction means, is 2 molecules, and I'm going to write it out. I know this is going to be excruciatingly long to do it this way, but 2 molecules of methanol react with 3 molecules of oxygen to produce 2 molecules of CO2 and 4 molecules of water. So that's what this reaction means. 2 molecules plus 3 molecules of oxygen give 2 molecules of CO2 and 4 molecules of water. But the thing is, we simultaneously have to picture this reaction in a different way, because we don't really run this reaction with 2 molecules and 3 molecules. We run it with a lot more than that, and we have to scale it up to things that we can measure. So simultaneously, this reaction written as is means 2 moles of CH3OH react with 3 moles of O2 to produce 2 moles of CO2 and 4 moles of water. And this is one of the things that makes introductory chemistry kind of hard, because we have to constantly be switching back and forth between these 2 ways of thinking about this. I'm gonna close my door here. Sorry about that interruption. And so we have to be able to constantly switch back and forth in chemistry between a molecular level view, something we can't see, we just have to picture, and a macroscopic view where we've got buckets of stuff, right? Beakers full of stuff. And this is proportional. We talked about the meaning of the mole and how we can scale things up. And it's, conceptually, at first at least, it's easier to picture 2 red things plus 3 blue balls go to 2 green things and 4 purple things, or something like that. You could have little marbles or little candies and picture that reaction, and you're just counting molecules, right? And so that's conceptually, I hope, very easy to picture. But when we're doing moles, what we have to get used to is that it's the same thing. Moles are still just a way of counting molecules, right? So 2 of these plus 3 of these give 2 of these and 4 of those. And moles are just a scaled up version of a way of counting it on a scale that we can measure in terms of grams. And so that's what we have to do. And then the other thing with the reaction is that reactions have to be balanced. And we'll talk about how to balance them in another video. But what that means is that a reaction, that's my abbreviation for reaction, RXN, is an equation. Okay, the law of conservation of mass says that we can't just disappear something. And so the number of carbon atoms, for instance, on the left has to equal the number of carbon atoms on the right. And a lot of then doing chemistry is this concept of stoichiometry and keeping those in balance and figuring out how much you can get from it. And so the total mass before we do the reaction has to equal the mass when we're done with it. It can't disappear. Now these are all gases, so it's a little hard to weigh them, but that's the idea. So let's see, a couple more things, and then we'll do examples with this. In terms of writing reactions, I think I'll do this again when we do balancing, but states of matter, we could have a gas, and then we just abbreviate that G. Could be a solid, we abbreviate that with an S. And then could be a liquid, that's just a L, and usually we try and do a script L because it doesn't show up very easily otherwise. And then it could be a solution, so it could be an aqueous solution. So an aqueous solution, you will just put AQ after it, okay? And so we'll include states of matter and balance it that way. So a reaction is an equation that is mass balanced and counting of atoms, it's balanced. So then, one other thing is we talked about the, the idea that the mass on the periodic table is the mass in AMU or the mass in grams if you have a mole. And so maybe I should rewrite that again here before I do the next thing. So this is review. This one we did in the last one. The mass on the periodic table is the mass of one atom, the average mass, right, in atomic mass units, and simultaneously it's the mass of 1 mole in grams. And at this point, you might have noticed I didn't say 1 mole of atoms. So that kind of gets understood after a while, right? That you're talking about 1 mole of atoms or 1 mole of molecules, but you're just counting the number. And so that's a really important thing to be able to switch back and forth. So an example would be, let's see, I've got my periodic table here. Let's look up, say, copper. I like copper. See if I can find it. It says 63.55 on the periodic table for its mass. And what that means is that it's AMUs for 1 atom of copper, and it's 63.55 grams are equal to 1 mole of copper. So that's the idea. And then when we start to have compounds or molecules in a reaction, then we have to talk about the mass of the whole thing. So we can have the molar mass, or sometimes I'll call it molecular weight. And that mass is just the mass of 1 mole of molecules. In grams. So for instance, we have our, let's see, what were our reactions over there? So we've got methanol, CH3OH. If we want to know how much that weighs, or what the mass is, we have to add that up, right? So we go to carbon, we look on the periodic table, we see that it's 12.01. And then we look up oxygen, we see that it's 16.00. I don't have to look these ones up because I've done them a billion times. And then we've got 4 hydrogens. So we have to take 4 times the mass of hydrogen, which is 1.008. Add all that up, and I could just use the round numbers on this one because it's close enough. But if I add all those up, let's see what we get. Okay, so I've got 12.01 plus 16 plus 4 times 1.008. And notice the calculator can handle that order of operations just fine. 32.04. So I get 32.04. So that is 1 molecule of CH3OH is equal to 32.04 AMU, or 1 mole of molecules, but we don't say that anymore. 1 mole of CH3OH is 32.04 grams. And then we can use these as conversion factors to go back and forth between grams and moles and grams and so on and so forth. Okay, so that's the idea. Now, that's for molecules, and we call it the molar mass. Now, ionic compounds are different, but we're going to treat them the same, right? We're just not going to call it the molecular weight because there aren't any molecules. So that would be the formula mass. So that would be something like, say we had sodium chloride, right? It's not a molecule of sodium chloride, but we want to know how much one of these weighs, 1 mole. So if we have 1 mole of that, we're going to add up the formula mass for that. The mass of sodium, the mass of chlorine, and we'll get 58.5 about for the total, 23 plus 35.5. And you can look those up. So we'll probably call that molar mass as well, but I won't call it the molecular weight because they're not molecules, or at least I shouldn't call it that. All right, so now I want to do a little bit of stoichiometry with this. So let's flip this over. And so with that reaction, let's go ahead and rewrite the reaction. Now you can look back and see it, but I need to have it on the paper for us to do it. So 2CH3OH, I'll leave out states of matter just to make it easier, plus 3 oxygen, 2 carbon dioxide, plus 4 waters. So that's the balanced reaction. We talked about the simultaneous meaning there. So we can do stoichiometry here. So let's first do this. What if we have, let me number them. So the first one, we're going to react 10 moles of CH3OH. And then we're going to ask how much O2 is required. Okay, so you get the idea here. Reading the reaction, we know that for 2 moles of methanol, 3 moles of oxygen are required. And so when it's whole numbers like this, I'm willing to bet that you could say, well, if 10 moles of this are going to react, then how much would I need, right? It would be, let's see, what would it be, 15? 15 moles. Does everybody see that? So 10 moles of this react, we'd get 10 moles of CO2, we'd get 20 moles of water. Would that make sense to everybody? So the reaction is always written in the lowest whole number coefficients, but you could scale it up. You could say 4 with 6, with 4, with 8. So you can go back and review this if that didn't make sense. Or 10 with 15 to make 10 plus 20. See how that works with whole numbers? So whole numbers, the logic, you can figure it out because we can work with round numbers. Our brains, or at least my brain, can handle it a little bit easier. But how would we do it in terms of a formal conversion? Because we're not going to be given whole numbers. I mean, we will some to check. So I usually do whole numbers like this to check the understanding, because I think, you know, that shows whether you understand the concept, right? But then the next part is calculating with not round numbers. So let's show the process for calculating this. Okay, so we're going to treat this just like a conversion, just like we're converting centimeters to meters, exactly the same way. And I know a lot of you can probably do this already, but I'm going to go through it in excruciating detail, just like we did with the first conversions. Okay, because I think, you know, some people will be helped by that. Other people maybe can skip over it. All right, so this reaction means that we want a relationship between the methanol and the oxygen. The reaction is stating that 2 moles of methanol are required, are equal to 3 moles of O2, right? That's what the reaction means. 2 moles of this will react with 3 moles of that. So those are equal. And so we can have conversion factors. Now, I suggest if you think you're having trouble with conversions or if you had conversion troubles on the test, go ahead and start with writing these out explicitly. It takes extra time, yes, but it will help you learn this process that's going to be so important. So when we divide through by this, we can divide through by the 3 moles, cancel it out. So we'll have 2 moles of CH3OH over 3 moles of O2. And now that would equal 1, correct? That's one conversion factor that we can use. Or we could divide by the moles of ethanol or methanol and bring that over. So that means we'd have 3 moles of O2 over 2 moles of the methanol. And that's equal to 1. So those are our 2 conversion factors. And pretty soon, if you do this a few times, you'll get the idea that we can have it either way. Now, some of you already know how to do this and you feel pretty confident about it. As your coach in chemistry, what I'm going to suggest is even if you think you can do this really well, and you probably can, if you would just commit to me that as your coach, you will always write the unit and the identity of the substance. So if you can do that, I'm going to write this. I usually just say this, but let's get it written down. Write the unit and the ID of the substance. If you can do that and treat those algebraically, cancel them out just like the factor label method, I guarantee you will do much, much better. You'll ace stoichiometry if you can convince yourself to do it that way. So now, we've got our conversion factors. We're always going to start with the thing that we're given, right? We're given 10 moles of CH3OH, and we're asked how much oxygen that would take. And so we look at our conversion factors and we look at one that will cancel with this. But it looks like that's in the denominator. So we'll take 3 moles of O2 over 2 moles of CH3OH. All right, now here's the deal. Of course, the key thing here, as with anything, whether it's math or physics or chemistry, is don't worry about what you have to do first or whether you might make a mistake, because it doesn't matter. If you do this with the units, you will always get it right, because let's say I chose the other one. Let's say I chose poorly. It wouldn't cancel out, and I would know I made a mistake, and I'm like, so what? I made a mistake. Big whoopee. I go back and do it with the other one, and then I get it right. So you don't have to sweat whether you make a mistake or not. And so 3/2 of 10, I hope, is 15. And that will give us our moles of O2. And that's the answer. All right. So what about if we had, instead of that, 0.15 moles of CH3OH? Well, it's the same process, right? 3 moles of O2 and 2 moles of CH3OH. And I just goofed here. What I should have done is asked you to pause and do it yourself, just like I would in class. I would actually pause for a while and maybe even walk around the room, but I goofed. So 0.15 times 3 divided by 2, and I get 0.225 moles of O2. Okay, so these are the types of problems that we have to know how to do from chapter 3. They are manageable. You can do this. Everybody can do this with just some practice, I promise you. All right, what about this? What if you're given a problem that says, should I turn that down? What if you're given a problem that says, instead, let's react 5 grams of the methanol, and then we're asked how many grams of H2O would we get. So switching, not worried about how much oxygen it requires, how much water would we get? Okay, let's see if I left enough room here to do this. Now in this one, I'm not going to show explicitly all the conversion factors. Hopefully you can go through and kind of reproduce those, and hopefully I left myself enough room. It's easier on the board where you can just go on to the other board. All right, so start with what you are given, 5 grams of the methanol, and then we need to convert between grams and moles. Well, that was that molar mass, right? That told us how many grams are in 1 mole of methanol. And if I look back, I can find that here. I did that, didn't I? So we had 32.04, okay? So we had 32.04 grams of methanol is the same amount of stuff as 1 mole of methanol. All right, now I knew to put the grams on the bottom because then it would cancel. But don't sweat it if you don't, right? Because if you tried it with it flipped, you would see it wouldn't cancel and you'd be like, okay, no big deal. I'm just going to flip it. Now I'm in moles of methanol. We want to get to the amount of water. Moles are the currency of chemistry, right? Moles are the amount. And so we want to get to the amount of water. We need to go from moles of methanol to moles of water. And so we go up to our reaction and we see that there are 2 moles of methanol will produce 4 moles of water. So go back down here and we go 2 moles of methanol will produce 4 moles of water. And again, I knew to put the moles of methanol on the bottom, on the denominator, so that it would cancel. But if you have your mole ratio flipped, your conversion factor flipped, it won't work, and you'll know it, and you're like, okay, I'm just going to flip it over the other way, and then it will work. Now we want to go from moles. They want actual grams, so the conversion between grams and moles is the molar mass. So I'll do that. I'm just going to do that in my head, and I'm going to use round numbers. So oxygen is 16, hydrogen's 1. There's 2 hydrogens, so that's 2 plus 16. So we're going to call that 18 grams of water is the same amount as 1 mole of water. And now we can do this all in one big long thing on the calculator, right? So we start with 5 divided by 32.04, and then times 4 divided by 2. Look, no parentheses, no nothing. My calculator can handle it just fine. Times 18, and I get 5.62. You always need 3 digits. 5.62, at least 3 digits. And that's grams of water. Okay? 5.62 grams of water. So this is a lot right here. Look what we've already done. We've learned in this one, maybe I'll flip it over here, keep going. What have we learned? We've learned the meaning of the reaction, that's both in molecules and moles. Okay, we've learned how to do the molar mass of a molecule by adding all that up. And we've learned to do some of what's called stoichiometry with reactions. So we've gone from moles to moles, and we've gone from grams to moles to moles to grams. Okay. And so I think I'll record the concept map in a separate one, but this is quite a bit. This is pretty powerful to be able to flip between all of these. Anyway, actually, should I do the concept map right now? Yeah. Nope, I'm gonna do it later. It's 30 minutes. That's a pretty good chunk of content, and I'll do a concept map separately. All right, thanks everyone. Let me know if you have any questions. Thanks.